This is from the 2011 AP Calc AB and BC Form B exams. This is the second version of the exam both years, but this was an AB and a BC question. And the setup is that there's a cylindrical can, radius of 10 millimeters. It's collecting rain over a 60-day period. They say the function s of t is going to measure the height of the water in the can at any day t across this 60-day stretch. We don't have s though. What we do have is the rate of change of s, or the derivative of s. So they give us that s prime of t is going to be equal to this, and this is going to again represent the rate at which the height of the rainwater collecting in this can is changing at any day t across this 60-second stretch within this town. First part wants us to say what the height of the water is at the end of the 60-day period. So if you need to figure out s of 60, we would take into account the initial amount of water in the can, which is 0, so that's why I don't really have it represented here, but technically you can think of it 0 plus how much the height has changed. And since this is the rate of change of height, if we integrate the rate of change of height across the appropriate limits of integration, we're going to have the value of this telling us how much the height has changed. Since we started with 0, all we really need to do to find s of 60 is evaluate this, and doing that on the calculator is something that should be pretty simple to do. We'll do it from the home screen again here just to kind of continue to review that process. So if you go into the math menu, you grab this numerical integration feature from the bottom of it. We need to first type in our integrand. So I'm going to swap out the variable t for an x just so it's easier for me to type in here. So that'll close my sine function, tack on the plus 1.5. That does it for my integrand. Now I need a comma, variable of integration, and the variable that I typed into the calculator was x, another comma, lower limit of integration, another comma, upper limit of integration, close that initial parenthesis, and there's your result rounded to 3 decimal places. So 171.8 millimeters would be the height of water in the can at the end of the 60-day stretch. In part B, they want to know the average rate of change of the height of water in the can. Well, there are two different ways you can think of this. A slope of a secant line, or a regular old slope calculation, will give you an average rate of change. So if we could compute s of 60 minus s of 0, and we actually already know this is the answer from part A, and then we actually already know this too. It said 0 was the initial height of the water in the can. So the answer from part A minus 0 is just going to be the answer from part A over 60 minus 0, which is an answer that you can get pretty quickly. If you weren't recognizing that you already had this computed, what you could do, since this is the rate of change of the height of the water in the can, you could use the formula for the average rate of change, or excuse me, the formula for the average value of a function. And since this function represents the rate of change of the height of the water in the can, the result to this calculation will in effect represent an average rate of change. So if you look at the formula and think about how it compares back to this, it's really going to be the exact same thing. This is the calculation that we did in part A. If I do 1 times this, I get this in the numerator divided by 60 in the denominator. So there are really two different ways to do this, and hopefully you see very quickly that both of them are going to be equivalent. You can either use average rate of change by taking the slope of a secant line, or you can use the average value of a function formula, since this function represents the rate of change of the height of the water in the can. Part C is a little related rates question. They say, assuming no evaporation occurs, find the rate at which the volume of water in the can is changing at time t equals 7 days. It wants us to indicate units of measure here as well. So I started with the volume formula for a cylinder, which wasn't really provided, so obviously that's something you'd have to kind of be able to come up with on your own. Hopefully it's pretty simple to do that. And we want to know the rate of change of the volume of water in the can. This would just represent the volume of water in the can. The rate of change of that is going to be the derivative of volume, dv dt. So I took the derivative of the left side of this, and then I also wanted to take the derivative of the right side. Now you'll notice that I don't have the same expression here as I had back here. Reason why is because this 10, the radius of the can, is constant. So I put 10 in place of the r since it doesn't change over time, squared it, got my 100, so it's just a simpler form of the right hand side of this equation. And then taking the derivative of the left side of the equation gives us dv dt, taking the derivative here. This is a constant, so it's going to be a constant within our derivative. And then the derivative of h with respect to t, since the height of the water in the can changes over time, is going to be this. And then we want to know what dv dt is evaluated at t equals 7. Well, dh dt, what they've been calling that throughout this problem, the rate of change of the height of water in the can, or the derivative of the height of water in the can, is given by s prime of t. So really, if you can compute s prime of 7, and if a calculator's in play, pretty simple to evaluate this on the calculator. 100 pi times this evaluated at 7 gives you an answer of this. Units, if you're concerned with them, and definitely not too difficult to think about here, you put 10 millimeters here and you squared it. So this 100 has units of millimeters squared the whole way down. This s prime of 7 is going to be the rate of change of the height of water in the can. Well, the height of water in the can is measured in millimeters, and then time is measured in days. So the units of this calculation would be millimeters per day. Take the product of the two, and you get millimeters cubed per day. And if you were asked to come up with the units that would probably make sense for this volume calculation, you'd probably come up with millimeters cubed per day. So it's nice that the units worked out the way they should have here. And then in the last part of this, and this is the trickiest part, they tell you there's a new town, and this town is also collecting water in a can, and the height of water in this town's can is going to be given by this formula. Now notice this is not a derivative, so this is not the rate of change of height. M of t is measured in millimeters, not millimeters per day like s prime of t would have been measured in. They define this other function based on both m and s, but notice this is an m prime, so we would have to take the derivative of m in order to compose d of t here. So I took the derivative of m, I realized this was a constant, so I just copied it down, and then I did the derivative of what I had within this quantity here, and then I just subtracted the original derivative that we've been working with all along from that, right? So I basically just wrote down a more specific definition of d of t. Rather than generally calling it m prime of t minus s prime of t, I've written out m prime of t minus s prime of t. We want to apply the intermediate value theorem, so they're kind of nice because they've told us what we're going to have to use to prove what we're asked to prove. But we want to use the intermediate value theorem on the function d with the interval 0 to 60 to justify that there must be a time at which the heights of the water in the two cans are changing at the same rate. Well, this is the rate of change of the height of water in the one can. This is the rate of change of the height of the water in the other can. If they're changing at the same rate, then this difference of their two rates would have to be 0. So what I did, and I think I have this on my calculator still here, I put d of t into the calculator, and then I manipulated my table so that in my table I could see what d of 0 is, copied it down right there, and then d of 60, copied it down right there. If we plot those points on a graph of d of t, 0, negative 6.75 is going to be here, and then 60, 69.377 is going to be up here. Now, as long as our function is continuous as we go from this point to this point, there's absolutely no way we can get from this point to this point unless we cross 0 at least one time in between. So is d of t continuous? That's the next question. Well, since this is the rate of change of the height of water in one can, and that rate is always going to be defined, and this is the rate of change of the height of water in the other can, and this rate is always going to be defined, yes, d of t is continuous on this interval, and there's no way to get from this point to this point with a continuous graph unless we cross 0, which is a value intermediate to this y value and this y value at least once in between. Now, it's very likely that the graph could maybe hit 0 several times, especially because of the sign component to this function, but the intermediate value theorem proves that at least one time you're going to have to cross 0 to get from here to here with a continuous graph.